So today I will talk about scalar and the vector field. So earlier I talked about that what is the meaning of scalar and vectors, or I can say that I talked about that there are two types of physical quantities like scalar and the vector. So today I will talk about the scalar and the vector fields. So first of all, let me talk about that what is a field. Because first of all we must know that what is the meaning of a field. So let me talk about mathematically. A field is a region. A field is a region in space in which a function f is defined at all points. At all points. Mathematically, I can say that f is equal to f, x, y, and z. It's a very simple definition. And what is the meaning of that? That the function is defined. Meaning of that function is defined. So it means that the function is continuous and is defined by a single value at every point of position variable. And in the layman of language, let me talk about that what is the meaning of a field. All of you heard about the magnetic field. Say there is a magnet. If I brought some magnetic needle near to it, then the region up to which it will influence this magnetic needle, say this is the region. So this is the field of this. This is the field of this magnet up to which it will affect this magnetic needle. And after that, this magnetic needle, if I place it here, this magnetic needle, if I place this magnetic needle here, then it will not affect it. So this is the simple definition of layman. So it's a region around something up to which it has some effect, right? It's a layman language. But mathematically, because magnetic field or electric field, these are up to infinity, they affect even gravitational field. They will affect things up to infinity, but their magnitude decreases as we go away from that, either from the charge or the mass object, right? So this is all about it, and this is a mathematical manifestation of it. Now, since we have two types of quantities, let me come back to here again. Since we are having two types of quantities, scalar and vector, right? So corresponding to scalar quantities, we are having the scalar fields, and corresponding to vector quantities, we are having the vector fields. So let me define now the scalar field along with the example. So let us talk about the scalar field. A region in space, in which a scalar quantity is continuous, quantity is continuous and is defined by A, and is defined by A and is defined by a single value at every point of position variable, is called a scalar field, right? So if phi is a scalar function of R, phi is scalar function of R, where this R vector is basically x, y, z in terms of Cartesian coordinates, then this phi can be written as phi x, y and z, right? Where phi is a scalar field. And let's try to understand it by taking an example. So consider a metal rod. This is a metal rod which I am considering, and say it is heated in some region. So near it, near this region, the temperature will be higher, and if we go further away from it, then in the farther away from this region, means from the rod, then temperature gets decreased like this. So basically we are getting these are the contours of different colors. So this is one contour, and this is another contour, this is another contour about which I am talking about. So as I go further away from this, temperature keep on decreasing, but over a particular contour the temperature will remain the same. That's what will happen, and it is same everywhere. So that means, let us try to understand the temperature field around a metal rod, heated metal rod. So heat is radiated. Since heat is, so sorry, first of all let me consider a metal rod and is heated. Consider a metal rod which is heated. So heat is radiated through this rod, radiated from this rod, and temperature near it starts increasing, and temperature near it starts increasing, and as we move further apart, as we move away from it, then what will happen? The rod the temperature decreases. So that means this is a rod, and inside this, say this is a one region, and here this is the temperature, and if I take another contour, so here say temperature will be T, then at this temperature should be T minus delta T, and so on. It keep on decreasing. That's what will happen. So it's a case of 2D, and here for the case of 2D I will talk about the contours. Contours means curves. Contours means curves. So what these contours will remain represent? So thus contour represents line of constant value of function or physical quantity here. The physical quantity is temperature. Here it is temperature about which I am talking about. But if rather than it is the case of 2D, but if it is a case of 3D, then we have to talk about the surface rather than a contour. So I will talk about these surfaces later on. These surfaces at which the value remains the same, these are known as level surfaces, right? And another example is electric potential. Another example of the scalar field is the electric potential. And electric potential at various points. Surrounding a charged body. Charged body is an example of scalar potential field. So suppose if I am having a charge, say this is a charge, and these are the electric field lines, and it is a spherical symmetrical. Then if I draw contours, so this is one contour, this is another contour. So for each contour, these are the potential surfaces. This is one surface, this is another surface. So if they are then at every every surface, this is one surface, this is another surface. Here they seems like a contours, but they are not contours, they are like surfaces. So for every surface the potential has the different value. Say at this value it is the potential V, and here it is the potential V minus delta V. So the potential will remain the same as we have seen for the case of the temperature nearby the heated rod. So these surfaces are known as equipotential surfaces. So thus there exists a surface passing through which all such points which have same value of scalar field, are called level surfaces. Are called level surfaces. And for the case of potential, is electrostatic potential, we call it as equipotential surface. Equipotential surface. So this is all about the scalar field. Now let us talk about the vector field. Vector field. So a region, let us define it, a region in space in which a vector quantity is continuous and is defined by a single value at every point of position variable. Every point of position variable is called vector field. So if E is a vector function or vector field, then this E can be written as E x y z. It is simple mathematical representation. So an example is if fluid flowing, its example is a fluid flowing along a tube of varying cross section. So let us take an example. Say it's a tube whose cross section is varying. So as we see that near the surface of the tube, its velocity of the fluid will be lesser, and as we move away from the center towards away from the surface towards the center, its velocity keep on increasing. Another thing, as the area of cross section decreases, its velocity is also increasing. That's what will happen, right? So that means the velocity of flow, or in other words I can say that lines of flow or flux lines. Flux means flow of something. Having both direction as well as magnitude. Direction and magnitude both. So, and the direction and magnitude, these two things are defined at every point. So this is the example of the vector field. Right? Electric field also another example of vector field. Electric field is also another example of vector field. another example of vector fields. Let us take an example. Say if we are having a source charge and it is a positive charge, and if I brought some unit positive charge, say this is a unit positive charge, if I brought it closer to it, then it moves in this way, it moves away from it, right? So in everywhere in the neighborhood of this positive charge, if brought it unit positive charge, it moves in this way, it moves in this way. So that means the electric field intensity every point, it will be different in different directions, right? So this is an example of this electric field about which I am talking about here is an example of the vector field, right? And this is the unit positive charge. So this is the source charge and this is the test charge. This is unit positive, this is simple convention, and it should be however small. So I will talk about this concept later on, right? So electric field is the another example. Similarly, gravitational field acting on a body, gravitational field acting on a body is also another example of the vector field, right? So this is all about the scalar and the vector field.